Okay, so now I'm going to add that 1 over omega squared line. And so it has that slope of minus 40 dB per decade. So I want to be, 1 decade would be a point out here. So I'm at 0.3, I go to 3, that's a 10x increase in frequency, 1 decade. And I would go to minus 40 dB. So what I'm going to do is I'm going to draw a straight line that goes like this. Okay, so this is my mass line, my 1 over m omega squared line. Okay. Now, the interesting thing is that I have these two approximations. I have my low frequency approximation where the system looks like a spring, and that's valid well below, turns out, well below something called the natural frequency for the system. And the system looks like a mass. Call this a mass line here. This is the spring line here. It turns out that these two things will intersect exactly at the resonant frequency of this system. Okay. This is omega n. And the reason for that is if we equate, essentially what we're saying where they cross is where these two things are equal. So if we write 1 over m omega squared is equal to 1 over k, we can rearrange that. We can write that it's omega squared is equal to k over m. And I'll put a little n on there, natural frequency. Okay? So that's really what a second order system looks like. It has a straight line at low frequencies, and then at high frequencies it has 1 over omega squared term, and so it has a slope of minus 40 dB per decade. Okay, if you remember, the first order systems have a minus 20 dB per decade slope. So second order systems have a slope that's twice as steep. And now what I'm going to do is I'm actually going to get rid of some of my construction lines that I used for this, because I am kind of walking our way through the description of the second order system. The actual second order system, I'll redraw this, it goes like this, and it goes to here. So this part here I'm just going to make dashed, okay, because that's not really what the second order system does. What it really does is it follows only the low frequency approximation below omega n, and it only follows the high frequency approximation above omega n. Okay, so I'll make this part of the line dashed. Okay, so that's my spring line. And what happens actually at resonance is totally dependent on the damping ratio. So in reality, we can get a resonant peak. So what's going on in there depends on the damping, and I'm going to call that depends on zeta, depends on the damping ratio. Okay. And similarly, in terms of the phase response, it's true that the phase will start out at 0 degrees and go to minus 180 degrees. So we get twice the phase shift that we would have gotten for a first order system. And the other thing that we know for every second order system is that at the natural frequency, so this is omega n here, omega n, the phase shift will be minus 90 degrees. Okay, if you remember, the second order system, sorry, the first order system had minus 45 degree phase shift at the crossover frequency. Here it happens to be minus 90 degrees, twice that amount. But what happens, the transition between the 0 degrees to minus 180 degrees depends entirely on zeta. Okay, so it'll do this, but what it does, it depends, how steeply it does that depends on zeta. Okay, and I'm going to show you a plot for that on the next slide. And just because we had numerical values, I might as well write it out. So if we look graphically at this plot, we would imagine that omega n is somewhere around 3 radians per second, right? Because it's clearly between 1 and 10, it's about 3 radians per second. And so we found that graphically, but let's actually plug in the numbers here. So omega n squared is equal to k was 90, divided by m was 10. It ends up being 9, and so omega n is 3 radians per second. Okay, so the graphical solution gave us the right answer. Okay, so what I did, the reason I did this example is I wanted to motivate a little bit more about frequency response, like where does it come from? And what I'm going to do is hang on just one second. Okay, so I took the Bode plots that are in the book for the second order system. This is the magnitude plot. This is actually figure 10.16 from the book. And so the way it's plotted is the frequency axis here is normalized to the natural frequency, right? So it's omega divided by omega n. And so you were going 1 decade below the natural frequency and 1 decade above the natural frequency. And you see the plot here is in decibels, right? 0, minus 20, minus 40. And so he's showing here the low frequency asymptote is a line at 0, because this is a normalized second order system. It has a gain of 1 at low frequencies. I picked one that had, it was not normalized, but this one is normalized. And then here's the high frequency asymptote. And so we'll notice on this one that this has a slope of minus 40 dB per decade. And you can see that you can get peaking of the magnitude response if zeta is small. So this is showing for zeta is equal to 0.1. We have a relatively large gain peak. It's about 14 dB peak here. And then as we increase the damping, so zeta is going up here, we start to get less of a peak in the magnitude. So when we're down here at zeta equals 0.5, we have a very small gain peak. It's maybe 2 or 3 dB. And then at zeta equals 0.7, again, you actually don't even get any peaking in the magnitude response here. But this is one reason you might want to think about, one reason why we would design a closed loop system to have a damping ratio of like between 0.5 to 0.7 is that we get a larger bandwidth out of this thing. And I'll talk a little bit more about what bandwidth means, but essentially it means the maximum frequency at which we get useful gain. If we have a damping ratio of 1 or greater, you can see that the gain is rolling off. It's less than 0 dB at a frequency that's maybe half of the natural frequency, right? So this is 0.1, 0.2, 0.3, 0.4, 0.5, right? So we have a significant reduction in gain at half the natural frequency. Whereas if we are operating with a zeta of 0.5, we get a gain out of this system that's greater than 0 dB up to the natural frequency, and then it begins to roll off at minus 40 dB per decade. And so what does this mean? If you're talking about this being an actuator, if we're applying a force to this thing and we want it to move, we need a lot of force to move out here where we are above the resonant frequency, and we need so proportionately less force to move. So that means we can move our mass very accurately down here, but up here where we're down by minus 20 dB, that means we need 10 times the input force, for example, to move this thing. If we're at minus 40 dB, we need 100 times the input force, and so we probably don't have an electromagnetic actuator that can do that. So that's one way to intuitively get an idea about bandwidth, is that we're going to talk about bandwidth being based on the minus 3 dB point, where minus 3 dB is measured relative to the low frequency gain. So we could kind of draw a line at minus 3 dB and see where all these guys cross it. More or less, we can, you can just sort of eyeball it and see that that when zeta is about 0.5 to 0.7, we're going to get the largest useful bandwidth without having peaking in the gain. And the peaking in the gain, we'll talk about this later on, that's undesirable because it's actually associated partly with ringing. Right? We know that it affects the settling time. And so usually we don't want these values of zeta because we have too much overshoot. We don't want these large overdamp systems because we have less bandwidth from our actuator. Okay, and I just wanted to go through a little bit more math on this. I apologize if that sounds scary, but also, and here's the phase response. So here's the phase response, again, plotted in the same way, frequency along the x-axis, phase in degrees on the y-axis. Starts out at 0 degrees, goes to minus 90 degrees, and how it transitions, they're sort of showing here that we could draw a line like we did for the first order system. If we drew a line at a frequency 10 times below omega n at 0 degrees and a frequency 10 times above omega n at minus 180 degrees, that would be our asymptote. But that asymptote is really only correct when zeta is 1 or larger. And if so, we have a damping ratio of like 0.7, 0.5 or so. Really probably should use the value from the table. We should use a lookup and correct our plot based on this figure. Okay, so I'm going to go back and I'm just going to go through the equations really shortly. So the mass spring damper equations of motion, hopefully these are familiar. We write as my double dot plus by dot plus ky is equal to the external force, and I called that U on the previous drawing that I drew, okay? So I have a term from the mass, from the damper, and the spring. So now I'm going to go through this exactly, okay, and I'm going to relate it back to what I said about the low-frequency approximation. Now when I see a differential equation like this, I want to take the Laplace transform. So I write ms squared plus bs plus k, whole thing times y of s is equal to u of s. And so we end up with the transfer function, which is y of s over u of s is equal to 1 over ms squared plus bs plus k. And so this is our g of s. Right? And so if you think about what we're doing here is we have an input, u, going into g of s. We have an output y. Okay? Now, let's talk about frequency response. Okay? To do that, I'm actually going to define some standard parameters, and I'm going to write this in the sort of normalized form. So I'll take out a 1 over m here. I have s squared plus b over m s plus k over m. Okay? And when I do that, I can write this as 1 over m times 1 over s squared plus 2 zeta omega n s plus omega n squared. Okay? So we have the standard version omega n squared is k over m. 2 zeta omega n is equal to b over m. Okay? So this is written in this sort of standard form for this thing. So this is g of s. Okay? Now, remember frequency response, we have g of j omega. I plugged in s equals j omega. Okay, and when I do that, I get 1 over m, 1 over, when I square j omega, I get a minus omega squared plus 2 zeta omega n times j omega plus omega n squared. Okay, and now I'm going to do a little bit of rearranging. I'm actually going to divide everything by omega n squared. Okay, and so I'm going to write this as 1 over m omega n squared. And then I have this other part here, and I get 1 minus omega over omega n squared plus 2 zeta times j times omega over omega n. That didn't quite fit very well, so I'm going to rewrite it. 1 minus omega over omega n quantity squared plus 2 zeta times omega over omega n. Okay? I'll put a 1 here. All right, so what I did was I divided everything by omega n squared. So when I do that, I get a minus omega over omega n squared. That's this term. This becomes 1, and that's this term here. And then the 2 zeta omega n times j omega, well, I divide, I get rid of 1 omega n, and so I need omega over omega n. And the reason I write it this way is that, if you remember, we normalized all the plots before to the ratio omega divided by omega n, right? If I go back to this response here, we're always using omega over omega n as a parameter. And so now we sort of have it in an actual form that looks like that. Now at low frequencies, we could say, we can be a little bit more precise about our definition of low frequency. That's omega less than omega n. Then what we're saying is that omega over omega n is much, much less than 1. And so if we look at this, this relationship here, and more or less all this complicated stuff here, well, it's all basically less than 1, and so we're just going to, it ends up that this whole thing looks like a 1, okay? So g of j omega at low frequencies looks like 1 over m omega n squared, okay? Which looks sort of complicated, but we remember that omega n squared is k over m. It's 1 over k. Okay, so at low frequency, this thing looks like a spring, and that's exactly what we started with at the beginning. Okay, and I'll finish the rest of it in the next section.